So now let's talk about the problem a little bit more. And specifically, let's talk about the two different ways of estimating the parameters. One is called the maximum likelihood estimate that I already just mentioned. The other is Bayesian estimation. So in maximum likelihood estimation, we define best as meaning the data likelihood has reached the maximum. So formally it's given by this expression here, where we define the estimate as argmax of the probability of x given theta. And so argmax here just means it's actually a function that would return the argument that gives the function maximum value as the value. So the value of argmax is not the value of this function, but rather the argument that has made the function reach its maximum. So in this case, the value of argmax is theta. It's the theta that makes the probability of x given theta reach its maximum. So this estimate intuitively also makes sense, and it's often very useful, and it seeks the parameters that best explain the data. But it has a problem when the data is too small, because when the data points are too small, there are very few data points, the sample is small, then if we trust the data entirely and try to fit the data, and then we'll be biased. So in the case of text data, let's say our observed 100 words did not contain another word related to text mining, then our maximum likelihood estimator would give that word a 0 probability, because giving it a non-zero probability would take away probability mass from some observed word, which obviously is not optimal in terms of maximizing the likelihood of the observed data. But this 0 probability for all the unseen words may not be reasonable sometimes, especially if we want the distribution to characterize the topic of text mining. So one way to address this problem is actually to use Bayesian estimation, where we actually would look at both the data and our prior knowledge about the parameters. We assume that we have some prior belief about the parameters. Now, in this case, of course, so we are not going to look at just the data, but also look at the prior. So the prior here is defined by P of theta. And this means we will impose some preference on certain thetas of others. And by using Bayes' rule that I have shown here, we can then combine the likelihood function with the prior to give us this posterior probability of the parameter. Now, a full explanation of Bayes' rule and some of these things related to Bayesian reasoning would be outside the scope of this course, but I just give a brief introduction because this is a general knowledge that might be useful to you. So the Bayes' rule is basically defined here and allows us to write down one conditional probability of x given y in terms of the conditional probability of y given x. And you can see the two conditional probabilities are different in the order of the two variables. But often the rule is used for making inferences of a variable. So let's take a look at it again. We can assume that P of x encodes our prior belief about x. That means before we observe any other data, that's our belief about x, what we believe some x values have a higher probability than others. And this probability of x given y is a conditional probability. And this is our posterior belief about x, because this is our belief about x values after we have observed y. Given that we have observed y, now what do we believe about x? Now do we believe some values have higher probabilities than others. Now the two probabilities are related through this one. This can be regarded as the probability of the observed evidence y here given a particular x. So you can think about x as our hypothesis, and we have some prior belief about which hypothesis is true. And after we have observed y, we will update our belief. And this updating formula is based on the combination of our prior here and the likelihood of observing this y if x is indeed true. So much for a detour about Bayes' rule. Right? So in our case, what we are interested in is inferring the theta values. So we have a prior here that includes our prior knowledge about the parameters. And then we have the data likelihood here that would tell us which parameter value can explain the data well. The posterior probability combines both of them, so it represents a compromise of the two preferences. And in such a case, we can maximize this posterior probability to find a theta that would maximize this posterior probability. And this estimator is called a maximum a posteriori or MAP estimate. And this estimator is a more general estimate than the maximum likelihood estimator, because if we define our prior as a non-informative prior, meaning that it's uniform over all the theta values, no preference, then we basically would go back to the maximum likelihood estimator, because in such a case, it's mainly going to be determined by this likelihood value here, the same as here. Okay, but if we have some informative prior, some bias toward certain values, then MAP estimator can allow us to incorporate that. But the problem here, of course, is how to define the prior. There's no free lunch, and if you want to solve the problem with more knowledge, we have to have that knowledge, and that knowledge ideally should be reliable. Otherwise, your estimate may not necessarily be more accurate than maximum likelihood estimate. So now let's look at the Bayesian estimation in more detail. Okay, so I show the theta values as just a one dimension value, and that's a simplification, of course. So we're interested in which value of theta is optimal. So now first we have the prior. The prior tells us some theta values are more likely than others. We believe, for example, these values are more likely than the values like here or other places. So this is our prior. And then we have our data likelihood. And in this case, the data also tells us which values of theta are more likely. And that just means those theta values can best explain our data. And then when we combine the two, we get the posterior distribution. And that's just a compromise of the two. It would say that it's somewhere in between. So we can now look at some interesting pointer estimates of theta now. This pointer represents the mode of prior. That means the most likely parameter value according to our prior before we observe any data. This pointer is the maximum likelihood estimate. It represents the theta that gives the data the maximum probability. Now this point is interesting. It's the posterior mode. It's the most likely value of theta given by the posterior distribution, and it represents a good compromise of the prior mode and the maximum likelihood estimate. Now in general, in Bayesian inference, we are interested in the distribution of all these parameter values, as you see here. There's a distribution over theta values that you can see here. P of theta given x. So the problem of Bayesian inference is to infer this posterior distribution and also to infer other interesting quantities that might depend on theta. So I showed f of theta here as an interesting variable that we want to compute. But in order to compute this value, we need to know the value of theta. In Bayesian inference, we treat theta as an uncertain variable. So we think about all the possible values of theta. Therefore, we can estimate the value of this function f as the expected value of f according to the posterior distribution of theta, given the observed evidence x. Now, as a special case, we can assume f of theta is just equal to theta. In this case, we get the expected value of the theta. That's basically the posterior mean. That gives us also 1 point of theta. And it's sometimes the same as posterior mode, but it's not always the same. So it gives us another way to estimate the parameters. So this is a general illustration of Bayesian estimation and Bayesian inference. And later you will see this can be useful for topic mining, where we want to inject some prior knowledge about the topics. So to summarize, we introduced the language model, which is basically probability distribution over text. It's also called a generative model for text data. The simplest language model is unigram language model. It's basically a word distribution. We introduced the concept of likelihood function, which is the probability of a data given some model. And this function is very important. Given a particular set of parameter values, this function can tell us which data point has a higher likelihood, higher probability. Given a data sample x, we can use this function to determine which parameter values would maximize the probability of the observed data, and this is the maximum likelihood estimate. We also talk about the Bayesian estimation or inference. In this case, we must define a prior on the parameters p of theta, and then we're interested in computing the posterior distribution of the parameters, which is proportional to the prior and the likelihood. And this kind of distribution would allow us then to infer any derived values from theta.